This year is a celebration it's very good. They actually say a lot of risk every time, so nothing's wrong with my record. It's on display, so you can tell them actually I had to get MRI done for them to go. Well, you didn't know at all. I like not at all. No, that's like my favorite. My mom was irritated about the whole entire yeah, because by the time they realized what was wrong with the items wearing a brace workout with me, and it wasn't, and I should have been pushing past, but
All right, so I can't read the calendar. Confused me. Turns out Good Friday is not what it is on my syllabus. Sorry about that. Tricky. So, right on my syllabus, it's on the wrong week. It's down there. That's not right. It's actually the week after that. So, there is no class on Good Friday, obviously. So I made a mistake on Monday. There is class on April 11th. Just kidding. Haha, fooled you. That's right. That was my pre-April Fool's joke. But that leaves us with a question about what to do about Exam 3. It is currently scheduled to be the day after Easter, which means you are going to spend Easter studying for my exam, which, looking at your faces, seems unlikely. So one option is we leave it for the Monday after Easter, because you've already planned around it. Option 2 would be move it to the Wednesday before Good Friday. So move it back a few days. Option 3 would be move it to the last week of class, which, up to you. Obviously, you're probably going to have like a million other exams that week. So think about it. Look at your calendars. I'll have a vote at the end of class. If we choose to move it to the last week of classes, you can always take it early. If it works out better for your schedule, you can always take a test early. So if it works out better because you have a million other papers, exams, term projects due, then that's fine. So take a few minutes, look through your stuff, and I'll have a vote at the end of class while I finish getting my act together up here. All right, so the last section of chapter 17 is talking about delta G naught and K and Q. We're probably going to be able to finish this up today and maybe start a little bit on chapter 18. depending on how speedy we are. Oh, and you'll need a calculator. So if you have your calculator out, go ahead and fish it out. We'll need it. All right, so as a reminder, right, we used K a lot in the last series of chapters, and K is our equilibrium constant. And as a reminder, right, we had reactions with a large K. Large K would tell us product favored. Reactions with small k would be reactant favored. So since K tells us about the directionality of the reaction, whether it's product or reactant favored, and G, delta G, tells us about the spontaneity of the reaction, which also tells us if it's going towards products or going towards reactants, they must be related. So, as our definition, our delta G of reaction is the increase or decrease of free energy as you're going from reactants to products. But as you know from experimentation, we don't always completely make products. It's not possible to have 100% completion of a reaction. We end up in kind of two categories. If we have a product-favored reaction, right, that would indicate that it's going to proceed largely to products. But not completely, right? Because you can't have 0 reactants left over at the beginning. Because what would happen to your K, your equilibrium constant, right? It's products over reactants. If you had 0 reactants left, what happens to your fraction? It gets crazy, right? You can't divide by 0. That's insane. So there's always some reactants left in every reaction. Or you can have reactant favored. But even in that case, right, you're going to have some products made even if it's reactant favored. So how can we determine if it's going to be product favored, reactant favored, and what the free energy change is going to be of that reaction? We are going to look at how Q, G, and K are all related to each other. So what's the difference between Q and K? Which one's Q? Right, Q is not at equilibrium, so it's any position we're at that's not equilibrium, where K is only at equilibrium. So if I have 2 reactants, I'm going to mix them together. I'm missing an F in that. They're going to proceed to a position of lowest free energy and then come to an equilibrium position. So we can mathematically describe this right, that's our position of lowest free energy. And it's going to be temperature dependent. And Q tells me that I may be at equilibrium, I may not be at equilibrium, I'm not exactly sure, so I have to use Q. So we use this equation to show that our delta G Standard state reaction, what's standard state for gases? right? 1 atmosphere. What's standard state for solutions? 1 molar. What would be standard temperature? All right, 25 or 298 Kelvin. Okay, so that's all standard state. But I'm saying standard state is affected by if I'm not at standard state. So this is this portion of it adjusts for the fact that I'm probably not at 1 atmosphere, 25 degrees Celsius, 1 molar. Very rarely will you have exactly standard state. So this is the part of the equation that adjusts for a different temperature. Let's see, we'll finish my sentence. All right, so delta G of reaction and LLQ are affected by the temperature. So when you're not at standard state, we calculate the delta G of reaction without the standard state portion of it. So that's good. I would also like to know about K, right? Equilibrium. So if I am at equilibrium, what is the value of delta G? Not standard state, delta G. We'll back up. If it is spontaneous towards products, is it negative or positive? It is negative, right? If it's spontaneous towards reactants, negative or positive? Positive. What if I'm at equilibrium? I should be at 0, right? Because I'm not positive, I'm not negative. The only value that's neither is 0. So at equilibrium, this is true, which means now I have 0. What do I change my Q to if I'm at equilibrium? Okay. And we'll rearrange that to get rid of that 0. So these are going to be the 2 equations you need to know for this chapter, above and beyond all the other ones we've done. These are the equilibrium reactions. All right, so let's talk about how delta G and K are related. All right, so if I have a delta G standard state reaction less than 0, my product favored or reactant favored? It's negative. Product favored, okay. So now I have a negative sign over here. So what does my value of K have to be to keep this half of the reaction, or that half of the equation, negative still? It has to be positive, so it's going to be greater than 1. Which makes sense with what we know about K. When we have a large value of K, which is anything bigger than 1, product favored. If it's smaller than 1, reactant favored. Delta G tells you the same information. So we can do the opposite case, right? If delta G, 0 of reaction, is greater than 0, now we have a positive on this side. That means this reactant favored, which means now my K has to be less than 1. Okay, well, if I'm at a point that K equals 1, where am I at in my reaction? I'm completely at equilibrium. What is the value of delta G standard state then? It has to be 0. So they tell you the same information, just depends on what your starting point is. Do you know the free energy and then find K, or do you know K and then find the free energy? but they both tell you about product versus reactant favored. So, because I love graphs, let's look at a graph. All right, so here I have increasing free energy going up the y-axis. And I'm looking at a reaction that starts reactants only and moves to products only. Right, so I'm traveling along this way. So if Q is less than K, it means I have more reactants than products, which means it'll travel this way to get to the point where Q equals K, which is a decrease in free energy, which also tells you that you're moving towards products. If I start at this end where I start with products only, I would have a Q greater than K, or which way am I doing? Yeah, Q greater than K, which means it has to travel back this way, which also tells you that we're moving from products to reactants to get to Q equals K. Maybe, yeah. Okay, good. All right, so let's combine everything into some sentences. So just like in this graph, right, the free energy of equilibrium is the low spot in the graph. So if you imagine you put a ball on this, it's going to travel probably all the way over here, then come back, and then eventually come to the low point in the graph. That's where equilibrium is. The lowest point of free energy will be where equilibrium lies. The delta G standard state reaction tells you where equilibrium lies, and it's going to tell you which way the reaction has to travel to get to equilibrium. So from this, let's see here. Do I have this on the next slide? Trying to figure out where I want to put this. Okay, I'll put it here. Okay, so continuing point 2. Right, so that's the equation we had before. The overall sum of the delta G reaction is the sum of the delta G times each of its stoichiometric coefficients products minus the sum of all the delta G of the reactants times the stoichiometric coefficient. That subtraction tells us delta G. Well, delta G also right, that's also true. That I could figure out delta G if I know enthalpy and entropy, because entropy and enthalpy will also tell me about the directionality of the reaction. Well, then we also now know, you guys will have a lot of equations on this next test. Right, now we just found out that the delta G is related to K. That depending on the position of equilibrium, they'll tell us about the spontaneity of the reaction, which way it's going to go. So that's all three of these equations tells about the position of equilibrium. If it's spontaneous towards reactants or spontaneous towards products, right? Because the sign that you get from this will tell you which way we have to go to get to equilibrium. Delta G can also describe the direction of equilibrium. Continuing my thought down here. Oh, I don't mean standard state here. Cross that standard state out. I don't want that one. This is just regular delta G. No standard state. So my non-standard state delta G of reaction tells me about the direction that I need to go to get to equilibrium. Because, right, I'm at Q, which Q is not equilibrium. So how this Q relates to this tells me which way I need to go to get to this one up here.
Wait, what about the sign for the ones up there? So delta G not, or what is it?
Yep, delta G standard state.
If it's negative, then it goes forward. Is that correct? Or is that like-
Yep, nope, that's true, yep. Yeah, so if these are all negative, then all goes towards product spontaneously. It's positive, then it goes towards reactant spontaneously, or it's non-spontaneous towards products, whichever way you want to describe it. All right, so if I have a negative non-standard state delta G reaction, it means I'm at a position where Q is less than K. If Q is less than K, then we're here on the graph, and we're going to spontaneously head towards products. Okay, now I have a delta G non-standard state greater than 0. Which means I have a Q greater than K. Which means I have too many products. So which way do I need to go to come back to equilibrium? I need to go back to reactants. Third case, because there's always a third case. Well, if I'm at a point that the non-standard state delta G is equal to 0, what does that tell me about K and Q? They are equal. So if I'm at the point where Q equals K, where am I at in my reaction? I'm at equilibrium. So if we know something about Q and K, we can figure out delta G, we can figure out which way we have to move it. If we know about delta G naught, we can tell if it's going to be spontaneous or non-spontaneous towards this. So we're going to do a bunch of practice problems to try and put that into action. And because I love graphs, the last slide is more graphs, but not everyone's a graph person. All right, so let's do, I think I have at least, we'll see how we're doing on time. I have definitely 2, maybe 3. All right, so let's find the non-standard state delta G of reaction given the following information. So I had carbon dioxide. Now it's carbon monoxide dichloride, something like that. I'm sure it has a better name than that. right, so given all this information, what equation do we know now that relates delta G? I guess there's only one reaction, only one equation you have that has plain delta G in it, right? It's this one. We'll know some more next chapter, but for now, just one. So delta G, make sure I get the signage right. Okay, so these are going to be the kind of homework problems that you're going to have. I know a lot of you enjoy just doing it on the calculator without writing anything down. These will tear you up if you don't write down all your steps on some paper, right? Because we're looking at you have to solve two different things and then plug it into a new equation. Because we got to find Q, and we got to find delta G, standard state, and then plug those into this. So it's kind of a multi-part, seemingly simple, but multi-part question. All right, so would you guys rather find delta G standard state or Q first? Delta G standard state, okay? So how do they go about finding delta G standard state? What's my equation for that in general? All right, the product minus reactants times their stoichiometric coefficients. All right, so we have 2 of that. I'd suggest playing along with your own calculator out there in the audience also, just to make sure I'm doing this right. Good so far? So based on just that, where does it look like we are lying? Or is this going to be spontaneous towards products or non-spontaneous towards products? Right now it's looking non-spontaneous. So we're going to see if the temperature has any effect on it, and then see if Q tells us anything about where we are in relation to K. Okay, so then let's find Q. All right, so it's products over reactants. What do I have to do to this? I gotta square that. All right, so now we're ready to plug it all in. I know Q. Ellen. thing that may trip you up is we just solved delta G up here in kilojoules, right? But this guy's in joules. So you may be off by a factor of 1,000 depending on which way you ended up going with that. All right, how do I feel about that? Pretty good? Fairly confident? Not terrible? All right, let's go right for the challenge question then. You good, Paul?
What, how did you type that in? I kept getting it wrong. I got like 8,000.
All right, so you got to do the natural log of the 28.4 first. And then multiply that times 298. And multiply that times 8.314. And that gets over here. Then you just add that to plus 4.6 times 10 to the third.
I still get 8,000.
Your calculator's acting crazy. Yeah. Yeah.
Stuff.
Okay.
Yeah, you actually get 8,000 if you don't multiply 46.9 times 10 to the third.
Oh,
I see.
yes.
You have to convert it to joules.
Yes, okay. There you go. That solved it.
Sorry.
No, you're good. You're good. All right, here's my challenge question then. All right. All right, so here's my given reaction. I've given you the equilibrium constant for it and the standard state delta G. I want to find the delta G at 3 different conditions. I want to look at standard conditions or standard state. I want to look at equilibrium, and I want to look at neither standard state nor equilibrium, some position in between. All right, so standard conditions, if I am a gas, what is my standard state? 1 atm. So if I wanted to find Q for standard conditions for a gas, what is my Q for a standard state gas reaction? 1. So first question, what is my Q in relationship to my K? Greater than, less than, equal to? Less than, right? K is up here. Q's here. So my Q is less than K. If Q is less than K, which way should my reaction travel? 2 products or 2 reactants? Should travel 2 products. All right, so then let's look at the delta G of reaction to see if that matches what we just said. right, what's the natural log of 1? So what happens to this whole portion? Goes away. So what is the delta G of reaction telling me about the directionality of my reaction? Is it spontaneous towards products or non-spontaneous towards products? It's spontaneous towards products. Good, because that's what Q and K told us. So these pieces of information should all tell you the same thing. If you find your information is conflicting, your math is off someplace. So since G is less than 0, means it's going to travel 2 products. All right, let's take a look at equilibrium. At equilibrium, how is Q related to K? They're equal. So using this equation up here, Q is now K, so what does that tell me about my delta G of reaction? It is 0, so we're done. We could plug it in. If you plugged in K for Q, you would find that these two values are equal, and they cancel each other out. Because if Q equals K, then delta G non-standard state would have to be 0. What does that tell me about the directionality? Is it going to go towards products or towards reactants? Neither. It's at equilibrium. It's done. I'm non-spontaneous in either direction. I'm at equilibrium. I've already made as many products and reactants as I'm going to make. All right. Now I'm at a position where I'm not at equilibrium, I'm not at standard state. This one right here. So I got to plug in my Q. What does that turn out to be? 1 divided by where am I in relationship to Q and K? Right, my Q is much larger than K. So what is my reaction going to do to get back to equilibrium? It's going to shift back to reactants or shift to the left. So let's figure out what G is and make sure that confirms that. And that's space at the end. All right, so if I get in the end a positive delta G of reaction, what does that tell me about the directionality of my reaction? Which way is it going to be spontaneous in? It's going to be non-spontaneous to products or spontaneous towards reactants, which is what our Q and K told us. So the G standard state, the G non-standard state, the Q and the K should all tell you the same information. Just depending on which one they give you, you find the other one just to confirm what you're going with. How do we feel about that? Pretty good, pretty good. It's a lot of plugging in, and really, you have to write down everything, otherwise you'll end up, especially these joules and kilojoules, you end up off by a factor of 1,000 pretty quickly. Or if you forget to write down your Q equation, you may forget a squared or a cubed or something, and then it's all off from there. Yeah, Rachel.
Will there ever be a situation where Q is greater than K, but the delta to give the reaction is negative?
No. All right, in that case, let's take a few minutes and start talking about my favorite chapter in the entire book. Just for a few minutes, and then we'll take a vote about the exam. All right, let's see here. All right, redox reactions and electrochemistry. So what sort of chemistry requires electrodes? Electrons. We're going to be looking at electron transfers. So oxidations and reductions change in the oxidation state. Best chapter in the entire book. All right, so electron transfer reactions is when we look at an interconversion of electrical and chemical energy. These are the most useful reactions, in my own personal opinion. Right, so these are the reactions that allow you to do work. These are the reactions that make you produce heat. These are the reactions that generate electricity for other reactions. These are the ones that you can use to complete a reaction. So it's a way of using a chemical reaction to produce work of a different form. So we can do this in two different ways. We can use what's called a voltaic cell. This is a cell that's spontaneous. It spontaneous products and generates electricity. And this is what you consider like your battery, right? This is your battery. That chemical reaction occurs inside your battery, and the byproduct is that it produces electricity to power your phone, things, whatnots, computers. Or we have the opposite. It's called an electrolytic cell. This one uses electricity to force a non-spontaneous reaction to occur. So right, you can have a non-spontaneous reaction, but if you change the parameters, it can become spontaneous. You change the temperature, you add energy, you change the concentration of reactants to products, you can force them to become spontaneous. In this case, we're going to use electricity to provide the extra oomph to get over the non-spontaneous. So this is electroplating. Anything that's electroplated, or silver plated, or graphite carbon fiber plated, those are all non-spontaneous reactions, but with electricity, you can force it to happen. So we're going to spend most of our time talking about voltaic cells, and at the very end we'll talk a little bit about these electrolytic cells and what they're useful for. All right, here we'll do just this one today. We'll warm up some baby electrochemistry. All right, here I have copper solid in a solution of silver ions, making copper ions and silver solid. So the reactants have changed oxidation states when they become the products. And for clarity, what we're going to do is we're going to split these into two what are called half reactions, so we can examine what's going on with one of the reactants and what's going on with the other reactant. So we're going to split the reactions into two what are called half reactions so we can better see what's going on. So I'm going to look at this one. And I'm going to look at this one. Right, so I've paired the same, in this case, element together. So I can look at just what's happening to the copper, and we'll look at just what's happening to the silver. All right, so in the case of the copper, what has happened to the oxidation state? Increase, decrease, stayed the same. I went from 0 to 2 as an increase. Right, I was at 0, now I'm at plus 2, so the oxidation state increased. If I was to balance this out with electrons, and electrons each carry a charge of -1, would I put electrons on this side or this side to balance the charge? Reactants or products? Products, okay. How many electrons do I need so that both sides have a charge, overall charge of 0? 2. So I've now made 2 electrons as a product. When you make electrons as a product, this is an oxidation half reaction. So 2 things tell you it's an oxidation. 1, oxidation state increased, and 2, electrons are a product. So an oxidation half reaction. All right, let's take a look at my silver. What has happened to my oxidation state? Increase, decrease, stayed the same. It decreased, right? I was at +1, now I'm at 0. All right, if I'm looking at these two, do I add electrons to the products or to the reactants to make them the same overall net charge? Okay, and how many do I need to add? Right, I got 2 silvers, each of +1, so I need 2 electrons to cancel everybody out.
So if there's like 2 in from the C, it would be 4?
Yes, yep. All right, so I used electrons. So I used 2 electrons as a reactant. We call that a reduction half reaction. So this chapter is going to be looking at overall reactions, splitting them into 2 half reactions, figuring out which one's oxidation, which one's reduction, and where do we put the electrons to cancel everybody out. All right, is everyone ready to vote? All right, so as a reminder, our choices are leave it for the day after Easter, move it to the Wednesday before Good Friday, or move it to the Wednesday after Easter. All right, I'm going to have you raise your hands just so I know for sure. Okay, how many people would like to leave it for the day after Easter? 0. Okay, how many people want to move it to the Wednesday before Good Friday? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and a half.
Does the date of the exam change how much material's on it?
No, it's going to be done in time anyway. So it'll be the same 2 chapters. I was just going to stretch it out. How many people would like to move it to the day after? Oh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, that's just 1. If you would like to take the test early, the test will be ready if you want to take it before Easter, if you have other things going on. So.